Good morning, everybody. So this morning I'd like to talk to you about a feature of the Diels-Alder reaction and of the Cope and the Claisen reaction, and also about a feature that getting into the lecture now, which is that of the molecular orbitals. Okay, and so that's what I'm going to talk about today. And then on Monday, we'll have a review for for next week's exam. But something we haven't had a chance to talk about, and that's going to become that is important for understanding the pericyclic reactions, and will be important for understanding the upcoming reactions of benzene, is that of molecular orbitals. The quantum idea is that an electron in an atom and in a molecule behaves like a wave. An electron isn't a particle inside a molecule, but rather an electron behaves as a wave. And waves have certain characteristics. One of them is that a wave has a region of positive deflection and a region of negative deflection. In other words, a wave, you're going up and you're going down, you're going up and you're going down. The positive deflection, that's the up. The negative deflection, that's the down. So you're going up and you're going down, up and down in a wave. Another characteristic of waves is that since the wave has a positive deflection and a negative deflection, there has to be a point at which the wave goes through a zero. So if you're positive, if you're up here and you have to go to negative, you're down here, you have to go through zero. You can't go from a positive number to a negative number without going through zero. So we can put all of this on a semi-quantitative footing by showing just a picture of a stereotype picture of a wave. And so you're going to have, there's the zero line, and you're going to have a region of positive deflection and of negative deflection and a positive deflection and so on. So that's the positive region, that's the negative region, that's the positive region. So all waves have this characteristic. Okay, so another characteristic of waves is frequency, and that is the time that it takes for successive troughs or crests to pass a certain point. And so if you can imagine, you're standing there, you're there, right, and here's a wall, and you're tethered, you're holding a string, and you're going to set up a wave in that string. And so you could do something that looks like this. There's my zero line. So you're bouncing that string up and down, up and down, up and down, up and down. You know, like at the gym, maybe you work out with those big ropes. Well, you're setting up a wave in that rope. And so you have a region of positive deflection, negative deflection, and positive deflection. Okay, but the situation that I picture here is that we would consider this a low energy situation. You're standing here with this rope and you're going long, 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 long. That's a low energy situation. You could do that all day. But now let's examine what the high energy situation would look like. Okay, I'm going to put that up over here. The high energy situation would be, well, here you are again. You're tethered to this wall by a rope. But now this time you're going to look at this high energy situation. There's your zero line. And this time, instead of long, 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 nice easy waves, now you're going to do whoa. You're putting in that's a lot of energy. That's a whole whole lot of energy to set up more waves in this in the system. So this is low frequency and low energy. This is high frequency and high energy. And a very important concept when we're dealing with waves is that as the energy increases, the wave has more nodes. This is fewer nodes. This is more nodes. And what is a node? A node is where the wave is equal to zero. It has neither positive deflection nor negative deflection. So there's a node, there's a node, there's a node, there's a node. So this low energy wave has 4 nodes. Okay, but now we look up here, and how many nodes we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9. A lot more nodes, representing that this is a higher energy situation, a higher energy wave, higher frequency wave than this. Okay, so a wave is going to have, just to summarize what we've said about waves, a wave is going to have regions of positive deflection, which can be associated with going up, which can be associated with positive algebraic sign, not charge. We're not talking about charge. We're talking about positive algebraic sign, and regions of negative deflection, which can be associated with the going down and negative algebraic sign. And the more nodes a wave has, the higher in energy it is. So these are just some of the characteristics of waves. And remember that an electron in an atom and in a molecule, they function like waves, and they're going to obey and conform to these principles. Okay, so now we've talked about some of the glittering generalities about waves. Let's talk about molecular orbits. Okay, so let me just illustrate this problem with ethylene. Ethylene is would be the most the simplest dienophile that we would see in the Diels-Alder reaction. So let's just go through what the molecular orbital theory of those pi electrons are. So pi MO theory of ethylene, which is this guy. Okay, first of all, we have to recognize how many that the MOs, the molecular orbitals, result from interaction. I'm going to call this the pi molecular orbitals because we're not talking about the sigma molecular orbitals. The pi molecular orbitals result from the interaction of p atomic orbitals. So in ethylene, this carbon here is sp2 hybridized. There's a p orbital there. This is sp2 hybridized. There's a p orbital there. So when these p orbitals interact, they form the pi molecular orbitals. P orbitals, they're atomic orbitals. The molecular orbital here would be the pi molecular orbital. Okay, and so for ethylene, N, which is equal to the number of p atomic orbitals, for ethylene, it's equal to 2. We have 1 p orbital on one sp2 hybridized carbon. We have another p orbital on the other sp2 hybridized carbon. So N is equal to 2. And the number of pi MOs is always equal to the number of p AOs. So that for ethylene, since two p orbitals are interacting, we're going to get two pi MOs. So this is also equal to, and they can be distinguished. These two orbitals can be distinguished in that we're going to have a low energy orbital and we're going to have a higher energy orbital. And how will these orbitals differ? They will differ in the number of nodes that each pi molecular orbital has. So I'm going to draw a little diagram here, energy diagram, right? So this will be energy, and this will be energy. Let's straighten this guy up. And so I have two p atomic orbitals interacting to form two pi molecular orbitals. The lowest energy orbital has 0 internuclear nodes. So the lowest energy orbital is going to have a, so there's one of the carbon atoms. There's one of the carbon atoms. Here's the other carbon atom, right? We're talking about ethylene. We're talking about the pi molecular orbitals of ethylene. And remember that thing with the string that you were tethered, that you were holding a string and you were tethered to a wall? Okay, so now these little dots, that could be you, and this could be the wall. Okay, and now the string is going to have in this lowest energy molecular orbital, it's going to have 0 internuclear nodes. And so that's going to be a wave that kind of looks like this, right? And this is all region of positive deflection. So now we want to picture the p atomic orbitals that get together, interact to form the lowest energy pi molecular orbital. Okay, and so there's one of our carbon atoms. His PMO, his p orbital looks like this. There's the other carbon atom. His p molecular orbital looks like this. But this wave here is positive deflection. So I'm going to arbitrarily assign a lack of shading to the positive part of this orbital, and I'm going to arbitrarily assign a shading to the negative part of this orbital. Okay, so this is the region of positive deflection. That's positive, and this is negative. Okay, and this has what I'm going to call the psi 1, molecular orbital 1. This has 0 internuclear nodes, and this is the lowest energy pi molecular orbital of ethylene, or ethyl, same thing. Okay, and so now let's look at the next molecular orbital, the next higher molecular orbital, which is now going to have one node, one internuclear node. So I'm going to call that one pi 2. It's going to have one internuclear node, and it's going to be higher in energy. So once again, just using this figure, there's you, there's a carbon atom right there, there's the other carbon atom right there, there's the wall. And now what I'm going to do is I'm going to draw a wave through the system that is going to have one more node than this one did. So that's going to look something like this. Oh, you see, there's my new node. There's my internuclear node. And if I want to draw what the p orbital looks like in this molecular orbital, it's going to go up here to touch the wave, and then have a load down there. This is going to go down here, touch that wave, and have a lobe up here. This is the region of positive algebraic sign, so that this lobe down here would be negative. And now the wave has entered a region of negative algebraic sign. So I'm switching up the shading. So that will be the next, that's what the next molecular orbital of ethylene looks like. It has one more node, and so that's going to make it a higher energy system. Okay. All right, now a little bit more vocabulary. Okay, so we have this guy. I'm just going to draw a line here. Get rid of this. I'm going to draw a line here that represents the energy level. And now to finish up this diagram, what I want to do is I want to feed electrons in, so that the ethylene, I have to find a home for 2 pi electrons. And if we remember back to Gen Chem, we know that the electrons occupy orbitals in order of energy, low to high. That's the Aufbau principle, right? And so I need to find a home for 2 electrons. And so I'm putting those 2 electrons in there. They live in this orbital. This guy is called the highest energy occupied molecular orbital. That is called the HOMO. And this guy is the lowest unoccupied, the lowest energy unoccupied molecular orbital. That's called the LUMO. Right, so maybe you've heard these terms, HOMO and LUMO. Okay. All right, so now let's increase the level of complexity. So this guy, this is the molecular orbital theory of ethylene. We want to refer this to that Diels-Alder reaction. So this would be the simplest possible dienophile. Okay, so now let's look at the simplest possible diene in the Diels-Alder reaction, which would be 1,3-butadiene. So molecular orbital theory of 1,3-butadiene. Right, and I'm going to draw the 1,3-butadiene in the C-looking shape that we always demand for the Diels-Alder. Okay, so what is N? How many P atomic orbitals are interacting, and how many pi molecular orbitals will result? Anybody have the answer? 4, correct. That's sp2 hybridized, there's a p orbital there. 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 So for butadiene, N equals 4, we have 4 interacting p orbitals, and we're going to have 4 pi orbitals. Let's draw them. Okay, so what do we do? We can draw them in a couple of different ways. One way, I'm just going to do it over here, and I'm going to erase it later. One way is to remember that string, the analogy of the string and the wall. And so there's one end of the string. There's our first carbon atom. Keep the spacing. There's our next carbon atom. There's our next carbon atom. There's our next carbon atom. We have 4 of them, and there's the wall over there. Okay, the lowest energy molecular orbital is going to have 0 internuclear nodes. So I want to hook up this dot with a wave that has 0 internuclear nodes. So the orbitals look like this. And this wave is all positive. So this lobe is negative, negative, negative. Okay, so I guess this could be, I'm going to come up with, I think, a very nice picture here. So I'm going to call this psi 1. Right, that's the lowest energy orbital. And now the next highest molecular orbital, it's this very same idea here. There's the wall. There's one end of the system. There's the first carbon atom. There's the second carbon atom. There's the next carbon atom. There's the fourth carbon atom. There's the end over here. And now I'm going to draw a wave that is going to have one internuclear node. So let's see. So it's going to be up, 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 down, 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 down. Oh, so that has one internuclear node. So it's a little bit higher energy. This is psi 2. And what do the p orbitals look like? Well, we draw this p orbital so that it touches the this wave that I've drawn here. See, they're not all the same size. If you look at your textbook and if you look at Professor Porco's notes, they represent these orbitals as all being as equally tall. That is not correct. This is positive algebraic sign, so it's negative down there. This is negative algebraic sign, and so this is negative up there. So that's what our next molecular orbital looks like. Okay, let's keep going. Psi 3, there's the end of the system. There's the first carbon. There's the next carbon. There's the next carbon. There's the next carbon. There's the next carbon. Looking like that. And now what we want is we want two internuclear nodes because this molecular orbital has a higher energy. So this is going to be challenging for me to draw in a free-handed way, but I'll try. Maybe look at something like that. And here's the positive deflection. Here's the negative deflection. Here's the negative deflection. And here's the positive deflection. Forgot to switch the phasing here. Okay, so that's what the next highest molecular orbital looks like. All right, now finally in that last psi 4, that's the highest energy molecular orbital. This is going to have 3 internuclear nodes. This one had 0, this one had 1, this one had 2. Now I need to draw one that has 3 internuclear nodes. First carbon, second carbon, third carbon, fourth carbon, fifth carbon. Okay, 3 internuclear nodes, huh? Wong, 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 wong. Something that looks like that. And the orbital is touching this curve that I've drawn here. The orbital is touching this curve that I've drawn here. Positive deflection, negative deflection, positive deflection. Positive deflection, negative deflection, positive deflection, negative deflection. Okay, and so that would be so this is a representation of the 4 high molecular orbitals of butadiene. Okay, so now that's his energy level, that's his energy level, that's his energy level, that's his energy level. Okay, now we need to feed electrons into the system. And how many electrons do we have to play around with? How many electrons live in the pi system here? 1, 2, 3, 4. So we have 2 pi bonds. A pi bond is 2 electrons. We have 2 of them. 2 times 2 is 4. So 2 of them going here and 2 of them going here. All right, and so now that is the HOMO. That's the highest occupied molecular orbital, and this is the LUMO, that's the lowest energy molecular orbital. Okay, this took a lot of time, so let me show you another way that you can come up with these orbitals that is maybe a little bit more, a little speedier. All right, so imagine we have, that's just my skeleton of butadiene, 4 carbons. I want 0 internuclear nodes. So this is this approach here. You can calculate the relative sizes if you draw this sine wave, but maybe you don't really need that all the time. 0 internuclear nodes. Now I want one internuclear node here. I'm going to draw a dotted line somewhere, but where? Symmetrically disposed. I'm going to draw a dotted line showing the presence of the node. In this more exact drawing, you see how the node is right between, right in the center. So I need to draw a dotted line there. That's going to be my internuclear node. And it's positive on this end, on this side. That's a node. We're going from positive to negative. So that's represented like that. Okay, next up. There's my butadiene skeleton. Now I need to find draw in 2 dotted lines representing 2 internuclear nodes. Where am I going to put them? I'm going to try to put them in a symmetrically disposed way. I'm not going to do that and that. That is not symmetrical disposition, right? So what I am going to do, I'm going to be guided by this diagram, and I see, oh, I have a node here, and I have a node there, right? Symmetrical disposition of these nodal boundaries. And so this is just a quicker way of coming up with those molecular orbitals. And finally, and at last, I have my highest energy molecular orbital. Now I need to draw 3 dotted lines, but I want to draw those 3 dotted lines in the symmetrical, pseudo-symmetrical way, so that we mean dotted there, dotted there, dotted there. So positive, negative, negative down there, positive down there. Okay, so these are 2 different ways of coming up with what the molecular orbitals are supposed to look like. All right, before we put this all together and talk about the molecular orbital theory and the Diels-Alder reaction, I want to make some comments about this pi molecular orbital diagram. Okay, so if we remember resonance, if we have butadiene, we can draw a couple of different resonance forms for butadiene. There's one of them. Draw this resonance form for butadiene. I can also draw another resonance form where I shot the electrons the other way. Okay, so there are the different resonance forms that I can draw for butadiene. Remembering that the actual structure of the molecule is a composite of these resonance forms. Right, butadiene never looks like that, it never looks like that, and it never looks like that. The actual structure of butadiene is a composite of all of these. So what this is saying is that this single bond is not really a single bond, it has some double bond character. this negative charge is canceled by this positive charge, and this positive charge is canceled by this negative charge. So when we want to draw a structure of butadiene as it really is, it's not that, it's not that, it's not that. It is actually none of those bonds are really double bonds, and none of those bonds are really single bonds. The resonance is telling us that this double bond has some single bond character. Resonance is telling us that this single bond has some double bond character. But the molecular orbital theory is telling us exactly the same thing, is that this molecular orbital is telling us that the electrons are free to move over the whole pi system. This molecular orbital is telling us, well, the electrons are free to move over the whole pi system, but there's a lot of interaction between carbon 1 and carbon 2. And there's a lot of interaction between carbon 3 and carbon 4. This molecular orbital is equivalent to this resonance form. It's saying you have a double bond on the left and a double bond on the right. You have a high interaction on the left and high interaction on the right. So the molecular orbital theory and resonance are equivalent statements of the very same thing. It's just that the language is different. In the molecular orbital theory, we're drawing these orbitals, and in resonance, we're drawing Lewis structures. Okay, so now let's put it all together. Okay, so what I have here, I hope you can see this, is that I've drawn the molecular orbitals of butadiene over here, and I've drawn the molecular orbitals of ethylene over here. And the Diels-Alder reaction and most reactions involve the interaction of a HOMO with a LUMO. And for the normal electron demand Diels-Alder, the highest occupied molecular orbital of the diene is interacting with the lowest unoccupied molecular orbital of the dienophile. And maybe you can see that this negative is that maybe you can see that this lobe here of the LUMO of the diene, whoops, is going to interact this guy right here, the LUMO. He's going to interact with this guy down here, the HOMO. And that's where those new bonds are coming from. This orbital interacts with that one to form a new bond, and this orbital interacts with that one to form a new bond, and there's the cyclohexane, ring. So two HOMOs can't interact with each other because they're filled up with electrons. Something that has electrons in it, the HOMO, is looking for something that doesn't have any electrons in it, the LUMO. And so that's why we have this HOMO-LUMO interaction. Okay, so now you try it. Draw the pi molecular orbitals of the allyl cation. What's our first step? First step would be how many p orbitals are interacting. There's going to be 3 of them, right? There's a p orbital there, there's a p orbital there, there's a p orbital there. So we have 3 interacting p orbitals. We're going to get 3 pi molecular orbitals. The lowest energy pi molecular orbital will have 0 internuclear nodes. So it's going to be something that looks like this. Positive, 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 negative, negative, negative. That's psi1. That's the lowest energy pi molecular orbital with 0 nodes. And now the next guy, psi2, is going to have 1 internuclear node. Where to put that internuclear node? I'm going to put it in a symmetrical disposition. I'm going to draw a dotted line representing that node. I'm not going to put that node over here. I'm not going to put that node over here. That is not symmetrical. Remember, I'm picturing a wave. I'm picturing a wave, and a wave doesn't look like that. I'm going to put it here, right in the center. And so the molecular orbital here has a value of 0, right? Because this dotted line represents the node, and the node is where the wave, the molecular orbital, or whatever, is equal to 0. So that's what the next highest molecular orbital looks like. Okay, so I have 3 interacting p orbitals. I'm going to have 3 pi molecular orbitals. So what does the third one look like? Third and highest one. It's going to have 2 internuclear nodes, right? 1 there and 1 there. So this is positive. This is negative. This is positive. Why am I changing the phasing? Because these dotted lines represent nodes where the wave is going from positive to negative. Has to go through 0. That's what's happening at the node. Okay, so there's the molecular orbital there. There's the molecular orbital energy level there. There's the molecular orbital energy level there. How many electrons do I have to play around with? How many pi electrons? 2, right? 1, 2, and that's a positive charge, meaning an electron is missing. So the orbital diagram with the electrons filled in would look like that. Okay, so now let's move up to the next level of complexity, which is pi molecular orbital theory of cyclic structures. For example, benzene. It's the very same approach. Pi MO of cyclobutadiene. Okay, so instead of a linear thing, now we're looking at a ring. Okay, how many p orbitals are getting together here? That's going to tell us how many pi MOs we have. So how many p orbitals got together here? Correct, 4. 1, 2, 3, 4. So for this guy, n is equal to 4. We will have 4 pi molecular orbitals. Okay, and so the lowest energy molecular orbital of cyclobutadiene will have 0 internuclear nodes. So this is going to require a little bit of artistry. Right, there's the rectangle of cyclobutadiene. There's a p orbital there. 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 and there are 0 internuclear nodes. So that's positive, negative down here. That's positive with negative down there. That's positive with negative down there. That's positive with negative down there. There are 0 internuclear nodes. That's the lowest energy molecular orbital of cyclobutadiene. Okay, now the next highest molecular orbital is going to have 1 internuclear node, symmetrically disposed, right? So here's my little triangle, here's my little rectangle. And now what I want to do is I want to draw a dotted line through this rectangle. That will represent my internuclear node, but I want to do it in a symmetrical way. So I'm not going to do this, right? What am I going to do? What I'm going to do is maybe something like that. Right, there's my internuclear node. This guy is positive on one end. And now when I go from here, I cross this nodal boundary. And so the phasing changes. And now when I go from here to this guy down here, the phasing doesn't change because I'm not crossing a nodal boundary. And so there's another molecular orbital of cyclobutadiene. But you know what? There are 2 ways of drawing a dotted line through a square symmetrically disposed. The other way would be, there's my rectangle. Instead of dot, 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 dot like that, where bonds are intersected, I'm going to draw a dotted line that cuts through the corners. This also has 1 internuclear node. And so I have my p orbital over there, and here I have another p orbital, but the phasing has changed. So that's another molecular orbital of cyclobutadiene, and since these have the same number of nodes, they are called degenerate. They have the same energy. Okay, so now the 3 down, 1 to go. The next molecular orbital is going to have 2 internuclear nodes. And so the question is, how can I draw 2 dotted lines symmetrically disposed through a square? There's my square. I need 2 dotted lines symmetrically disposed. There they are. And so this is going to be positive up here. Flip the phasing. Flip the phasing once again. And flip the phasing once again like that. So that's the highest energy molecular orbital, and that's going to have 2 internuclear nodes. That's higher. Okay, so now it's time to feed electrons into the system. How many electrons are we dealing with? We're dealing with 1, 2, 3, 4. So remember Gen Chem, you have Aufbau and Pauli exclusion. Remember all that 1s2, 2s2, 2p6, jazz, remember all of that? So the electrons occupy the orbitals in order of energy, low to high, no more than 2 electrons in any orbital. That's Pauli exclusion. And then we also have Hund's rule, which is we have to maximize the number of spin-up electrons while satisfying Aufbau and Pauli exclusion. So we have 1 electron in here and 1 electron in there. I could represent them with upward pointing arrows. I'm not going to get into that. Okay, so that would be the diagram for cyclobutadiene. Okay, so now I want to finish up by talking about the pi molecular orbitals of benzene, but because this takes a whole lot of artistry, I'm going to modify my approach a little bit. So for this guy here, for example, what I'm going to do is instead of trying to draw these orbitals like this, I'm going to put my eye up there, and what I see is the tops of the p orbitals. So instead of just drawing these p orbitals with the two lobes and all of that, because that's going to take a lot of time, it takes more artistry. I'm just going to look down on the system, and all I can see are the tops of the orbitals. And so this open circle here, that represents the positive algebraic sign of this lobe. This closed circle here, this represents the negative algebraic sign. See what I'm doing? I'm just looking down on the system. Okay. So now we're ready to talk about the molecular orbitals, pi molecular orbitals of benzene. How many pi molecular orbitals are we going to get? 6, because we have 6 interacting p orbitals. 1, 2, 3, 4, 5, 6. The lowest energy pi molecular orbital of benzene is going to have 0 internuclear nodes. Open circle, open circle, open circle, open circle, open circle, open circle. This is the very same thing, but I don't want to keep drawing it this way because it's going to take forever, and this is going to be ugly and messy after a while. That's the very same thing as that. 0 internuclear nodes. The next highest molecular orbital is going to have 1 internuclear node symmetrically disposed. The question is, how can I draw a dotted line in a symmetrical way through a hexagon? So there's my hexagon. I want to draw a dotted line through that, symmetrical, like this. Positive over here, cross the nodal boundary, negative over here. But there's a second way of drawing a symmetrical dotted, there's a second way of drawing a dotted line through a hexagon in a symmetrical way. And so I see I have a degenerate orbital here. Instead of up and down like this, I can do this. Positive up there, negative down here, negative down here, negative down here. Okay, so for pi, for benzene, n equals 6, 3 down, 3 to go. Next guy is going to have 2 internuclear nodes. How can I draw 2 dotted lines symmetrically disposed through a hexagon? I could do this. Positive, negative, positive, negative. But there's another way of drawing 2 dotted lines through a hexagon. And that will be an X. Positive, positive, negative, positive, positive, negative. So once again, I see 2 degenerate molecular orbitals. Okay, last is now I need 3 internuclear nodes. How can I draw 3 dotted lines symmetrically through a hexagon? That's going to be my highest energy orbital here. 1, 2, 3. Positive, negative, positive, negative, positive, negative, positive, negative, positive, negative. Right, and so there's my highest energy molecular orbit. And so this is what the orbitals look like. Now let's feed in electrons. 6 electrons. 1, 2, 3, 4. Right, I'm following Aufbau principle, Pauli exclusion, and Hund's rule. 5, 6. And so that would be my occupation diagram. Okay, and so now here's an important, the whole reason that we go through this, the whole reason anyone would care about this, is that we know that benzene is very thermodynamically stable. It has this property of aromaticity, and we want to have an explanation for why benzene is thermodynamically stable, and we're looking at it right here. This has, benzene has a full shell. Just like on the periodic table, you know, why are helium, neon, xenon, why are the noble gases, the group 8, why are they so stable and so unreactive? Because they have full shells of electrons. Helium has a full 1s shell. Neon has a full 2p 2s and 2p shell, and so on down the periodic table. That's why those noble gases are so unreactive and so stable. It's the same explanation for benzene. We have a full shell, and that's what confers the stability. Okay, so that's all I have for you today. Any questions about anything before we sign off? Any questions about anything? Okay, I'll see you on Monday. I'll see you on Sunday for my office hours, and on Monday for a review.